us started. So, to get us going here today, I will draw your attention to this chart of data. If you take a look at this chart of data, maybe for a minute or so, maybe less than that, probably take you a minute, hopefully, based on the numbers there, you can probably figure out a way to describe the motion of the object that we're measuring here. What's happening to this object as it's moving? Figure it out. It's going 0.5 meters per second, and you can figure that out because you look at all the position measurements, and they go up by how much? 0.5, and the time that we took those measurements occurred every 1 second, and so you go 0.5 meters per second. Okay? Not too hard, right? However, if I showed you this graph, right, could we come to that conclusion maybe a little bit faster than we did by just examining the data table? Maybe a little bit. Maybe not the 0.5 part, but could we conclude possibly that this object was moving at a constant velocity maybe a little bit faster than trying to examine that data? Probably there, right? And it'd probably be even faster if I gave you this, right, where I added in that best fit line, right, showing you that trend that is occurring in the data over time, right? So, we start off with this. To kind of introduce us to this idea of graphing motion, or helping us to visualize what's going on in a physical situation using a graph to get that visual representation, right? Most people are going to see trends and patterns a little bit quicker visually than we will just by kind of combing through those numbers. Some people are savants and they just see numbers and like whatever, right? But, you know, most people, that visualization helps. Another thing that the visualization helps with is the first data table that I showed you, there were only 6 measured data points. 6 times, 6 positions. But there were a lot of other positions and a lot of other times that this car, or whatever motion it is, I don't know, car, probably not, it's only 0.5 meters per second, but whatever. This object, there were a lot of other times and a lot of other positions that this object was at, and at certain times. We didn't actually measure them, but we could make a pretty educated guess about where this object was at, say, I don't know, 3.5 seconds. Okay? There we go. At like 3.5 seconds, we can make a pretty educated guess about where that position was based on the line that we put on that graph. Or we could make a prediction about what would happen at future times if we assume that the trend continues. The easiest one probably would be, right, after 8 seconds, what could we probably predict about where that object would be if the trend would continue? At 4 meters, right? Assuming again, right, the trend continues and stuff like that, right? So this graph, this visualization of position and time data helps us hopefully visualize that motion a little bit better, or explain it a little bit better. If you would like, let's turn to page 54 of your book. Page 54 of your book is the beginning of section 2.3. You also have these things here on the sheet that I gave you today, so if you don't have to, you don't have to if you don't want to. Yeah. That was authoritatively we closed that book as well, so you can't tell me what to do with this. All right. Reviewing what we just talked about. Graphs help visualize motion. One of the reasons that we make graphs is to look for patterns and look for trends. And that's easier to do with a graph a lot of times than it is with a data table. This specific kind of graph, right, we are going to plot position on the y-axis and time on the x-axis to create a position time graph. crisis averted. So, all right. Down at the bottom, just like the graph I showed you, graph of position versus time. Then on page 55, this picture up at the top here, I gave to you at the bottom of the first sheet of your packet. Gathering additional information from a graph, even though we only measured the red dots that show up on this graph, we can make predictions about where the object was at places other than those red dots based on the trend and the line that we put in there to represent that trend, right? Then at 2.5 seconds, we could probably assume that it was around 1.25 meters because of the trend in the numbers that we actually measured. But one thing about this graph specifically, and it happens in a lot of other graphs too, but one thing that we're going to catch on this graph is that even though we measured specifically where an object is at what specific time, sometimes we can get more information out of that graph than just the two factors that we measure. So let's go back to this picture here. Right? Back in pre-algebra, I think, you learned about slope. And slope is defined as rise over run. And then maybe when you got to algebra, we got a little more sophisticated in our definition of slope. And we define slope as the change on the y-axis over the change in the x-axis. Right? These are all mathematically how we define the slope of a graph. Okay? But that applies to a regular x-y axis. Right? In math class, it can just be the y-axis and the x-axis, whatever. But here, we're actually measuring stuff. Right? On our y-axis, we're measuring position. On our x-axis, we're measuring time. So these generic x, y variables that show up in our definition of slope actually mean a little bit more on this graph because they're actually representing something. Let's start with the x-axis. What are we representing or measuring on the x-axis? Time. So in this definition of slope, instead of delta x on the bottom, we can plug in delta t to represent the change in the time. On the y-axis, we're representing position, right? But more specifically, not just where the position is, but slope talks about the change in the position. That's a term we introduced last week, and we called it displacement, okay? Now, here's where I don't want you to get confused. What symbol did we use to represent displacement? Delta x. This delta x here is not the same as this delta x here. Okay? This delta x is just the generic x-axis on a graph. This delta x is the change in the position on the position time graph specifically. Unfortunate that it's the same letter, but do we understand the difference between the two? Okay. That being said, if we have change in position over change in time, again, that's a topic or a concept that we introduced last Friday, and we call that the what? That's the velocity. Delta x over delta t is the average velocity. So on this graph, even though we only measured the position and the time, we can tell the average velocity of this object based on not the measurements we took, but the trends in the measurement that we observed from the graph itself. And as it states on page 55, average velocity can be determined graphically, specifically by the slope on a position time graph. If we go back to this picture representing that original set of data that I showed you at the beginning, right? Here, in this box, right, it gave us the slope of this graph as 0.500, and they even added after it meters per second, right? Hopefully we remember, again from Algebra 1, right? Because this is a linear graph, a straight line representing the trend, y equals mx plus b, right? The m representing the slope, so when we put m in there, 0.5, right? And Krista, we originally said at the beginning, just by looking at those numbers, we could tell that this object was traveling at 0.5 meters per second. Here, with the units, right, as meters per second, right, if we go back to using this definition of slope, we found out that on this graph specifically, if we apply the delta y over delta x concept to this graph, we get displacement over time, or velocity. If we look specifically or exclusively at the units, right, or let's go here, on the y-axis, what unit are we measuring in? Meters. And then on the x-axis, what unit are we measuring in? Seconds. So if we apply just units to this, we end up with meters per second, which we know is the unit that we use to measure for velocity. Okay? So that's why this graph in particular makes that jump, because when I put the data in, I told that it was meters on the y-axis and seconds on the x-axis. Good. Brett, go ahead. Not necessarily. I mean, that's how you could do it. Sorry, I should say this. You're going to have to calculate the slope of certain parts of the graph. I don't care necessarily if you show me all of that work. You just have to do it. So if you can do it in your head, which for the graphs, especially at the beginning of this section and for the homework tonight, they're pretty simple graphs. If you can do it in your head, that's fine. But it's going through and just demonstrating that point, right? That it's, in order to calculate delta x, technically we do x final minus x initial. So, you find out where it ended up at the 2 meter mark minus where it started at the 1 meter mark over the time that it took to do that. They're just mathematically going through and showing you. All right, while this graph is great, it's pretty boring. On page 56, get a little bit more exciting. Some changes to those graphs. All right, let me do this actually. All right. So this is the graph on page 56. Here. All right. So those two sections, similarities and differences. What can you describe? What's similar about the two motions there? What's different? Luke, tell me what's similar first.
They both have a positive slope.
They both have a positive slope, meaning that they both have a
Positive velocity.
meaning that they are both. What makes them similar? They both have a positive velocity. They're going in the same direction, right? That's how they're similar, right? But they're different because, how are they different? They're both traveling in the same direction, but, go ahead, Ray. Which one's faster, green or purple? Purple, because it had, what do you see about the slope of purple? It's steeper, it's more positive, right? So purple is traveling faster than green, even though they are traveling in the same directions. They both have positive slope. Okay. Can you tell me about pink? Slope is 0, because what kind of a line is it? Horizontal line. Horizontal lines have slopes equal to 0, right? If we think about it just from what the graph is telling us, if we think about this section of the graph as being a bunch of ordered pairs, what would you see about the y values of all the ordered pairs in that pink section of the graph? They'd all be the same, meaning what, right? Because the position keeps coming up the same over and over and over again. If the position's the same, it's not going anywhere. That section, what happens? Two things happen. Go ahead. Change direction, so now it's going which direction? Negative direction, okay? Is it on the negative side of the origin? No, it's just traveling in the negative direction, right? What else can you tell me about the blue section compared to green and purple? Can you tell me about blue compared to green and purple? So it's the steepest, meaning that it's going the fastest. Even though it's going in the negative direction, it still has the highest speed. Okay. Good? All right. Open up your book to page 57. If you would, please. Okay. Shouldn't just mark orders at you. On page 57, let's start with question number 31. So question number 31 has two parts, A and B. It says rank these motions in order of increasing speed, rank these motions in order of increasing velocity from most negative to most positive. There's a little bit of room at the bottom of the back of that page. If you just want to do it right there, that's fine. In the sheet that I gave you today. If you want to do it on a separate sheet, that's okay too. If you just want to do it in your head, that's fine too. Okay. So, answer those two questions. Let's take about a minute, and then we will come back and discuss. All right, so let's discuss the answers to these questions. All right, first, part A. Rank these motions in order of increasing speed. Luke, speed only tells us what about an object?
The magnet.
Of speed describes what about an object?
How fast it's going.
How fast it's going, without regard for
Direction.
which direction it's going. So, does the tilt of these lines matter at all? Does it matter whether they're sloping up or sloping down?
No.
Not for part A, it doesn't. Okay? So if we're looking for increasing speed, we want to start with the one that is the slowest. Which of these four is the slowest? C is the slowest. Which one's next? B. Then A. Then D. So that is the order of increasing speed. Doesn't matter which way that line tilts. Just give me like crystal ball, right? That has multiple choice test question written all over it. Okay? Which of these four lines is going, or which of these four objects is going the fastest? Right? Doesn't matter, right? Speed doesn't matter which direction it's going, just the slope of the line. But for part B, rank these motions in increasing velocity from most negative to most positive. Now, if we're talking about velocity, we have to take into account which direction they're going. So which one's the most negative? D is the most negative. Then C, even though it's the slowest speed, right, it's still more negative than any of the other ones that are left. Then B there? Okay. Let's take a look on that same page at questions number 33 and 34, because they relate to the same picture. Alright, so 33 and 34. It says, a small gauge train moves slowly back and forth along a straight segment of track. Position time graph for the train is shown below. Before we answer part A and B, tell me something about the motion of this train. Anything that you can interpret from the graph that shows up there. Brett, what's one thing? Okay, it changes direction.
Good afternoon. One more brief end of the day announcement. We will be having a homeroom schedule tomorrow. Homeroom schedule tomorrow. Thank you.
So it changes directions. Brett, how many times does it change direction? It only changes direction twice. Was that a guess, or do you know a lot?
No,
Okay. Changes directions there, and it changes directions there. Why? Because it goes from what kind of slope to what kind of slope? Positive to negative, or the second one goes from negative to positive. Okay. What else can you tell me about this train? Where does it start? Does it start at the origin? Does it have to start at the origin? Not necessarily. Okay. All right. For part A, it says which section, A, B, or C, does the train have the smallest speed? So what are we looking for? Smallest speed. Smallest slope. Luke, can you make an educated guess as far as which one has the smallest slope? This one's not quite as obvious as the previous picture. But B. Then for part B, it says what is this smallest speed? If we're looking for speed, right, it doesn't have any regard to direction. But to calculate the speed, what do we need to know? How do we calculate the speed of something? Distance over time. So during part B, what's the distance that train travels? 3 meters. Why, Luke? Because it starts where?
at 2.
Okay.
1.
Starts at 1, but it ends up at
4.
The distance is on the y-axis, right? Because y-axis is position. So it starts at the 1 meter mark, but it ends at the negative 2 meter mark. That's a distance of 3 meters. Okay? Distance being scalar, it doesn't matter which direction it's going. Okay. Time that it takes to go that 3 meters? Okay. What's the velocity of the train during that section? Negative 1.5 meters per second. Good there? Okay. Real quick, for homework. Oh, it's going to be tight. Alright, here, here, here. Alright. For homework, the end of chapter 2. Numbers 74 through 78. And then 80 and 81. All kinds of questions very similar to the ones that we just did. Answers are posted down at the bottom. Okay? I will see you guys tomorrow.